Hey guys, I just want to put together this little tutorial video to walk you through how to navigate the parent graph and transformations virtual foldable. So we're going to go through each of the 4 different parent graphs and then each of the 10 different transformations. So this will be a little bit of a longer video, but feel free to jump around and find kind of where you need assistance with. And really once you kind of get used to the navigation part of it, you'll have access to this all the time. So you can go through and be able to navigate to and from different transformations to go through those and get more assistance on those. So this is the first page. So I have this in presentation mode, which you guys I would suggest doing. It makes it easier to navigate to each individual piece that you might need. You can present this, and then there's an option down in the bar at the bottom that lets you have it full screen, but just within a tab. So that makes it easier to kind of multitask. You can kind of click and drag it over to one side of your screen and then have whatever you're working on the other side if you're doing something on the computer. So that's an option as well. But this is what the first slide looks like. And this is going to be the home page for this slideshow. Because what I set up is each of these different words, they're underlined and kind of faded in blue. Each one of these is a clickable link that will take you to a different slide in the slideshow, in the presentation. So we're just going to go through each one of these, and I'm just going to kind of walk you through the 4 different parent graphs, and again, those 10 different transformations and kind of how we do those. All right, so let's go ahead and start with a constant graph. So that's our first parent function. So we click on constant. This is all the information you could possibly need for all the different functions. So for a constant function, this is the equation for the parent graph. It's just f of x equals 1. That's just a constant, right? No variable or anything like that. So in here, this is a table of values. I gave you guys all the table of values from -2 to +2. So all I did here was take these different values, plugged it into my equation for x, and got an output back out. So in this case, since it's just a constant function, just a constant equation, there's no variable to actually plug it into. All of my outputs are just +1, which is why we get this horizontal line here at +1. And that is the one thing to be careful with for a constant graph. It does start at +1. It doesn't start at 0 as others do. So that's the one thing you have to watch out for, because this is where my constant function starts. So if I have any transformations off of this, it's based on this being the starting point and then my end point being wherever it is. But again, we'll go through those, and I've got different examples for all 4 of the functions. Graphing tip here. Again, this is just a horizontal line that starts at +1. So that's how I would graph my constant graph parent function. So we can go ahead and click back here to go home. Let's take a look at our linear function next. For a linear function, the parent equation is just f of x equaling x. So that means for my table of values, when I evaluated from -2 to +2, since x is the only thing in my equation, I just get x back out for my y values. Which is why we have this graph looking like this, where all of my x and y values are exactly the same. So from -2 to +2, my outputs are also -2 to +2. So for this one, again, my parent graph version of a line, the y-intercept happens at 0, 0. It's at the origin, and the slope is just +1. So from 0, 0, you can just go up 1 over 1, up 1 over 1, and then just connect those dots to graph it. For an absolute value, this is what our parent graph looks like for an absolute value. It's kind of that V shape. That's my equation, just the absolute value of x. Here we know if I'm evaluating any number, absolute value basically just makes it a positive of that same value. So -2 becomes +2, -1 becomes +1, and then the other 3 just stay the same. So for the graphing tip here, my vertex, which is the point of my absolute value, starts at 0, 0, and then I have a slope of 1 on either side. So technically the right branch has a slope of +1, the left branch has a slope of -1, but really, once you have that vertex at 0, 0, or wherever it's going to be, you're just going to go up 1 over 1 on both sides. So up 1 over 1 on the right side, up 1 over 1 on the left side. And that's how you would graph the parent graph for an absolute value. All right, so let's look at quadratic as our last parent graph that we'll look at for this chapter. For a quadratic, and my graph here is not perfect. It was a little difficult to try and get it on the computer with it overlaying appropriately, so I had to kind of create a curve and it did this weird thing where it kind of belled out at the ends. It doesn't usually do that. It usually follows this same curve, so it really should be closer here rather than kind of how it flared out at the ends, but same general idea. And you can use the points that we'll evaluate in order to graph those things, and that's what I would actually suggest. So since my parent graph is x squared, that's what a quadratic is, my variable is squared, all I have to do here is just square those x values to get my y values. So negative 2 squared is 4, negative 1 squared is positive 1, 0 is 0, 1 is 1, and then 2 squared is 4. So if you look, if I plotted these points, 0, 0 would be right here, 1, 1 would be here, negative 1, positive 1 is here, and then negative 2, comma 4, positive 2, comma 4 gives me those points. Now, those points are graphing shortcut for doing that we learned back in Algebra 1. Remember, I called that the 1-3-5 shortcut. So for a parent graph, and for most of them, unless we're getting shifted around, my vertex for a parabola happens at the origin, just like the absolute value graph does. So I'm going to start here at 0, 0. And then to get each branch, each side of my parabola, I'm just going to go up 1 over 1, and I plot that point right here. I can go then up 1, 2, 3 over 1, and plot my point there. If I had a bigger graph, which most of the time you will deal with, I can then go up 1, 2, 3, 4, 5, and over 1, and that would be my next point, and I could continue going. Basically, the pattern here, if you didn't notice, we're just going up by odd numbers. So I would go up 1 over 1, up 3 over 1, up 5 over 1, up 7 over 1 if I wanted to continue. My vertical part of my parabola is the thing that's those odd numbers, and that horizontal change is just always 1. So I'm just always going over 1. So that's the graphing shortcut that we have for a quadratic. So now getting into our transformations, I have this arranged very purposefully. If you look here, all of my top row, these are all vertical changes, and all of my bottom row are all horizontal changes. And that's going to be important, and we'll kind of look at the pattern for where different operations happen. In general, if we're dealing with a transformation that's going to change our graph vertically, whatever operation is happening, whether it's going to be addition and subtraction, which is going to be translations, whether it's negative signs, which is our reflections, or whether it's multiplication, which is our stretches and our shrinks, if that operation happens on the outside of my function, it's going to be a vertical change. If it happens on the inside of my function, it's going to be a horizontal change. And we'll look more specifically at what I mean by inside my function versus outside my function. So let's just start here at vertical translation up. So for our example here, for a vertical shift up, which I use shift and translation interchangeably, that's okay to use if you don't know. If you aren't comfortable spelling translation all the time, or you just would rather use the shorter word and just say it's a shift, that's fine with me. I'm not going to take points off if you say it's shifted instead of translated. Translated is the technical term, but shifting is still fine. So this is what I mean by operations happening on the outside of my function. So here, f of x, that's just my parent function. So in this example, we're using a constant graph. So f of x equals 1 is my parent graph. So if I add something to my function on the outside of the actual original function, that's going to change it to be a vertical shift. So in this case, going from positive 1 to positive 3, I'm just shifting that graph up 2 from the original function. Just like I usually would, I'm going to graph my parent graph first, which is right here at positive 1. And then to shift it up 2 to positive 3, I'm just going to take any or all of those points and just count up 2 units, up 2 units, up 2 units for all of them across the board. Really, for a lot of these, you can just do that for a single point, so you get kind of the positioning of that new function, and then you can just kind of, again, draw a horizontal line straight across. This down here is always going to be how you would describe this, because some of the problems will give you a description of the transformation or give you the equation to say, hey, graph this, which would be this part over here. Some of the problems will also ask you to describe the transformation based on the equations. So in the structure of this foldable, this last part here right above the go here to go home or click here to go home button, this is always how I would describe this transformation. A description always includes three different elements. The first one, you have to tell me what kind of transformation is happening. The second part is which direction is that transformation happening. And then the third part is what magnitude, or by how many. So in this case, shift up 2 is as simple as I can write it. Shift tells me what kind of transformation is happening. Up tells me the direction. And then 2 obviously tells me my units, my magnitude. The flip side of this, if we take and subtract some value off of my function, so again, this is happening outside of my function, that's going to cause that shift to happen downward. So here, if I'm subtracting 4 from my original equation, because f of x equaling my absolute value of x is my parent function, my parent equation. So if I'm subtracting 4 from that value, that's going to shift my graph down 4. So here you can see my blue graph is my parent function. That's just my standard absolute value graph. The graph here that's just listed as graph, that's my transformed version. So I've taken and subtracted 4 off of that, so you can see the result for my red graph is that I've been shifted down 1, 2, 3, 4 units. I'm not changing the orientation of it. I'm not changing how tall or how wide it is or anything like that. I'm not rotating it. All I'm doing is just sliding it down 4 units. So again here, this would be my description. Shift down 4. Short and sweet. Sticking with our translations, let's go to horizontal. Now this is where it starts to get a little bit weird, because for any horizontal movement, any horizontal change, it's the opposite of how you would usually expect it to happen. All right, if we look back at shifting up, that was just adding. If I was shifting down, that was subtracting, which makes sense. Adding is going to move it up, subtracting is moving it down. Horizontals act in very weird ways. They are the opposite of what you would usually expect to happen. Because here, if I'm trying to shift it to the right, that actually appears as a subtraction on the inside of my function. So inside of whatever that operation is for the function I'm dealing with, if I see it as a -3, that's actually shifting it to the right 3. And it's a weird kind of rationale on why that happens. Because if this is my parent graph, basically what we're saying for any x value, I'm stealing the y value from 3 spaces to the left. So basically here, if I'm looking at, let's just say 0, and this blue one is my original function. If I'm looking at my transformed graph, which is x minus 3, for this x value, I'm going to count 1, 2, 3 to the left, and this y value happens here, right here at -3. That y value becomes the y value back over here at 0, which is why my red graph happens right there. And I realize that's a little bit weird that we're stealing from 3 to the left and dragging it to our new position, but that's why a -3 looks like a shift to the right. Because here, it's not pushing it to the right, it's actually pulling it from the left. So for shifting it to the left, now again, we're going the opposite of what we would expect. Shifting it to the left on my graph would be losing value, right? We're going backwards 1, so we would think we were subtracting 1. But again, since it's horizontal, it's happening on the inside of my function. Now I'm actually going to be adding k, so adding some number. And whatever this k is, that just tells you what that shift is. So again, opposite of what we'd expect, x plus 1 actually means to the left 1. So I'm just taking this original blue parabola, that was my parent graph, and shifting it to the left 1 space. And again, for these, I'm going to just start with my vertex. I'm just going to start here, left 1, and then I can just use my same shortcut to graph the rest of the pieces. I don't have to necessarily shift every single point on my graph in order to shift my graph. Description, also the same as our other transformations so far. I have to list what kind of transformation is happening. So here a shift, I'm telling the direction of left, and then the number of 1. So that's our translations. Vertical up would be plus something on the outside. Vertical down would be minus something on the outside. Horizontal to the right would be subtracting on the inside. And then horizontal to the left would be adding on the inside. So now in the middle here we have our 2 different reflections. And for a reflection, that operation that's happening is just a negative sign. So we're just flipping the value of my original function. So same as we had before, vertical is going to be on the outside of my function. So if the negative sign happens outside your function, either outside a parenthesis or really not inside a parenthesis or inside of like those absolute value bars, we get to assume that that's a vertical change. So here, if I have a negative on the outside, that's just going to flip it vertically, which is over the x-axis. So in this case, my blue graph is my parent. In this one, we're looking at a quadratic, so we're looking at a parabola. That's the blue. If all I have for my change is that I'm adding in a negative sign in my function, that's just going to flip it vertically. So it's going to flip it over the x-axis, which is how we get this red graph. For this, you've got a couple of different ways you could do this. For a parabola, you could still start with the vertex at 0, and instead of going up 1, 3, and 5, you could go down 1 over 1, down 3 over 1, down 5 over 1. Or if you already have the parent graph plotted, you've already got this blue graph graphed here, all you would have to do to reflect it over the x-axis, you just take this point and count how many spaces it takes to get to the x-axis, and then you count the same number on the other side of the x-axis. So here for this point that I'm looking at, 1, 1, if I was going to reflect that over the x-axis, I'm going to go, okay, it takes 1 unit to get to the x-axis, so 1 unit on the other side would be that point. Or here, 2, 4, if I reflected that over the x-axis, I'm going to count down 1, 2, 3, 4 units to get to the x-axis, 1, 2, 3, 4 units on the other side of the x-axis. And then just, again, connect your dots to draw your nice smooth curve. I have two different ways that I can describe this. I can be a little bit more formal and say it was reflected over the x-axis, or I'm okay with you just saying it was a vertical reflection. Just be prepared to see either of those. The book tends to use the fancier term. So if they're describing a transformation to you and they say, here are these transformations, it was shifted down 2, left 1, and it was reflected over the x-axis, just be prepared to be able to graph something like that or write an equation based on that description. But if you're graphing it and then just describing the transformations that happened, I'm okay with either of these two. For our horizontal reflection, which is over the y-axis, basically the same thing. It's just now it's a reflection over that vertical axis, so it looks like a horizontal flip. And just like we've seen before, since it's horizontal, that negative sign is going to happen inside my function. So if the negative happens inside the parentheses, inside your absolute value bars, or anything like that, it's a horizontal flip. So here my parent graph was just x, just a linear function. And here, since it's inside my parentheses, that negative sign makes it a horizontal flip. So here, my blue graph is the original, and all I'm doing is reflecting over this y-axis instead. So you could think of it as the line has a slope of -1, or if you're going to do a little more old school, like we just did in the last one, just pick a point or two, and then just count the units to the y-axis, and then units on the other side of the y-axis. So here, this point 2, 2 is 2 units from the y-axis, so then 1, 2 more units on the other side is where my reflected point would be. Be smart about this. When you should know when we're graphing a line, you only need 2 points. And even better, if it's only a reflection, if I'm already on the y-axis, that point stays the same. So really for these, all you would need to do is find one other point to reflect. It still goes through the origin, as long as it's just a reflection. Our description is very similar. I can say either it's reflected over the y-axis, which again, my y-axis is this vertical one, or I can just call it a horizontal reflection. I'm fine with describing it either way, but again, just be prepared for the book to describe it to you using that fancy reflected over the y-axis. Okay, so our last set is probably the trickiest, the thing that people struggle with the most, and it's stretching and shrinking. So technical terms for these would be dilations. This is probably what you called it back in geometry. Here we just call it stretching and shrinking. The operation that gives us a stretch or a shrink is going to be multiplying. And again, where that multiplication happens determines which direction I'm stretching or shrinking, and whether it's a stretch or a shrink. So if I'm multiplying on the outside of my function, it's going to be a vertical stretch or a shrink. If I'm multiplying on the inside of my function, it's going to be a horizontal stretch or a shrink. So let's take a look at vertical stretch first. For a vertical stretch, you can see the structure of my function is that I have a some number multiplying on the outside of my function. And what tells me that it's a stretch is that my a value, that number I'm multiplying by, is bigger than 1. If you're multiplying by something bigger than 1, it's going to stretch it out and make it taller than how it usually is. So you can see here my parent graph is just +1, so I'm dealing with a constant. So this one's a little bit unique because it's a constant. There's no, you don't see a function, you just see numbers. So you kind of have to determine or decide whether you want to call this a stretch times 3 or a shift up 2. Really, I would accept either of those. They're both correct. It's just your personal preference on what you want to call this. How I handle stretches is the same, no matter what kind of function I'm dealing with. I'm going to start with my regular parent graph, in this case +1. And the way that I get my new points is that I take my original y values on my graph and just multiply it by whatever this a value is. So in this case, we can obviously see that 3 is what I'm stretching by, because 1 times 3 is 3, so my a value is 3. So I'm taking all of these y values and just multiplying it by 3. This is easy in this case as well, because all of my y values are 1, so now if I multiply those by 3, they're all just going to be +3s. So my description for this one, vertical stretch by 3. So this one, we kind of flip the order of those 3 elements. So here we tell whether it's a vertical or horizontal first, but then we say whether it's a stretch or a shrink, and then we have to describe the factor by which we are stretching or shrinking. So whatever this a value is, which is 3, is going to be that factor. So we're stretching vertically by 3, vertical stretch by 3. Looking at a vertical shrink, this one we are starting with a linear function, that's our parent. So here, same basic structure, I'm still multiplying on the outside, so that tells me it's still a vertical. But because my a value is between 0 and 1, that's what tells me that it's now a shrink. So it has to be between 0 and 1. It can't be 0. It can't be +1. It has to be between those two. And here, notice I didn't just say less than 1, because the number itself has to be between 0 and 1. If I go smaller than 0, that starts being negative, and that could actually be a combination transformation. So like if it was like a -3, that's both a reflection and a stretch by 3. So that's why we're just talking about the actual digits here, just the actual numbers. If that a value is between 0 and 1, that's what tells me that it's going to be a vertical shrink. So it's making it shorter than what it usually is. So in this case, again, my parent graph is just x. I can see that my multiplier, that a value, is 1/2. So all I'm going to do is take all of these y values on my function and just multiply them by 1/2, or easier way of saying that, just divide by 2. So I'm going to just use the easy ones. So this point right here was originally 2, 2. So if I cut that y value in half, now that's 2, 1. Or 4, 4 divided by 2 becomes 4, 2. Again, just a vertical change, so it's only those y values that are changing. It's only those y values that are going to be shrinking. Description is the same. I'm still going to say it's vertical. I still have to say that it's a shrink, in this case by 1/2. Our last two are definitely the trickiest two. But luckily, it's the two that we see the least often, but it's still something that we have to be aware of and still something that we might see pop up. So let's take a look at our horizontal stretches and shrinks, starting with our horizontal stretch. When we are stretching something horizontally, that is still multiplication happening, and it's still on the inside, which matches everything we've seen so far. Right, inside is horizontal, outside is vertical. Stretching and shrinking is a multiplication. So again, it's opposite of what we would expect, because those smaller numbers are going to actually stretch our graph horizontally, whereas our bigger numbers are going to shrink our graphs horizontally. Again, it's very weird. It's opposite of what you would think in both ways. So the example here that I gave, if we're dealing with an absolute value graph, which is just the absolute value of x, which is our nice blue V shape here, with our slope being up 1 over 1 on both sides and the vertex at 0, 0. If now our A value is a third, again, it's opposite of what we would expect. So instead of actually shrinking our graph horizontally by a third, we're going to do the opposite of that. So the opposite of 1/3 would be 3. I'm just going to do the reciprocal. I'm just going to flip it over. So if I'm stretching now by 3, horizontal is going to be my change now. So my y values will all stay the same. It's those widths that are going to change. So now for my original point right here, 1, 1, if I multiply that x value by 3 from the 0, 1, 2, 3, happens right there. So my new x value is 3, still with my y value of 1. I could do that with other points. They just don't fit on this graph in particular. As you can see, it gets wider than what it usually is. So description-wise, same as you would expect. I have to tell you that it's you have to tell me that it's horizontal. You have to tell me that it's a stretch, and you have to tell me by what factor. Now this is the part again that's confusing because I see my a value as 1/3 in my equation, but since it's stretching it 3 times wider than what it usually is, that's the value I have to use in that description. For the last one, our horizontal shrink, since it's a stretch or shrink, still going to be a multiplication. Since it's horizontal, it's still on the inside, and it's also opposite of what you would expect. So on the vertical stretches, those values were bigger than 1. In this case, my a value being bigger than 1 makes it a horizontal shrink, making it narrower than what it usually is. So here my parent graph I'm starting with is a quadratic. It's x squared. If I multiply by 2 on the inside of that function, that actually tells me that it's going to get shrunk horizontally. So it's going to be by a factor of the reciprocal of 2, which would be 1/2, which is why I have a vertical shrink by 1/2. Same idea as my horizontal stretch. I'm going to just take these x values for any point on my graph and just cut my x values in half. So you can see here 1, 1 becomes 1/2, 1. 2, 4 becomes 1, 4. And I could keep going for my other points. But really, again, as long as you have a couple of points on your graph for a parabola, the minimum that I want is 5 points. So again, starting at the origin and then 2 on either side, that's what you would need for the minimum. I know that was a lot of information. Take your time and feel free to rewatch different things. I would especially focus on the ones that you struggle with. I think for most people, these translations are very easy. They're just shifting around. And really, even the reflections are not too bad either. It's really going to be focusing in on the stretching and shrinking that's going to take the most to get used to. And that's okay. We're going to spend a couple of days on this. Don't freak out if you're confused. Take your time, ask questions, rewatch this, go through the slideshow and kind of familiarize yourself with it, and let me know if you have any questions. I will see you guys soon. Have a good day.